Okay, quick review from Friday then. Ideally, you did this from memory, but if you needed your notes, that's fine. How are delta x and dx related? They are equal to one another. They are the same value. They are equal. Delta x represents the change in x on the curve, also the change in x on the tangent line. Okay? So delta x, because they're the same, represents the change on the curve, the horizontal change on the curve, and on the tangent line because they're the same. Okay? Because delta x is also dx. Delta y represents the change in y on curve or tangent. Curve. With that in mind, maybe curve is actually a better answer up here, but since they're the same, we won't distinguish. Okay? And then dy represents the change in y on the tangent line. Okay? Now, we were trying fifth hour today to come up with a clever way to remember that delta goes with the curve and d goes with the tangent. I'm open to suggestions at another time. Try to make them humorous. I thought it would be kind of fun to incorporate Delta Airlines into it if you can do that in some way. Because anytime you can connect, we love to fly and it shows with mathematics. Isn't that Delta? We love to fly and it shows. Come fly the friendly skies. Corporate logos, corporate slogans, those aren't any good anymore, are they? Okay, so we're going to take that idea and we're going to extend it just a little bit. Now, today's lesson is not going to be earth-shattering in any way. It's going to be very similar to things you've already seen. We're just going to put some specific notation on it, and we're going to solve problems in a little different way that you haven't done before. But really, all we're doing today, guys, is finding equations for tangents. And you've done that before. Question or comment? Delta is what? We love to fly and it shows. I knew it. From 1987 doesn't make me feel old at all. Not at all. You guys weren't alive in 1987, were you? That's okay. That's okay. That was a couple years ago. What is the ordered pair? So you can read through the introduction of this. We've got a curve. We've got a curve f of x. We've got a tangent line that's shown in green here. We've got an x value of a. What is the ordered pair? We don't know what the curve is. What's the ordered pair? What's the x value? A. And if we don't know what the curve is, what's the x value or the y value? F of a. We'll just use notation for that at this point. Okay. What notation would we use for the slope of f of x at a? F prime of a. That's what makes this a derivative application. We're in chapter 4, which is applications of the derivative. There's why it's a derivative application, because it involves f prime. Okay? So, using these three things, what is the equation for the tangent line that has that as its slope and that as its point? Do you remember? In general, I'll write down this. That's point slope form for the equation for a line, right? Let's apply what we know in this scenario to it. Y minus f of a equals f prime of a times x minus a, right? What is this? That is an equation for that green line. Okay? Even though we don't really know what the function is and what the derivative is and all that, but that is an approximate, or that's an equation for the green line. And we talked on Friday that if we work with values that are close to a, kind of in that green circle area, if we work with values that are close to a, looking at this picture, I think it helps. Looking at your page might help too. But what do you know in this region about the green curve, the green line and the blue curve? They're approximately the same. Okay? The point of this lesson is we're going to use this linear equation. Even if we don't know anything about the function, we're going to use the linear equation that represents the tangent to approximate function values. What that allows us to do is if we have a nasty function but we know something about its derivative, we can approximate the function values. Party tricks like we did on Friday. What's the square root of 99? You're going to learn that before the end of the hour again today. We're going to do square roots again. Okay? So this is, I think it's, the formalization I think is on the bottom page of your notes. It's at the top here. So if we were to solve that equation for y, we are going to introduce a new notation, a new letter really. L of x is going to represent a linearization. It's an approximation of a curve. And I know a couple of months ago we did an activity where we took a curve and we zoomed in on it. It was that local linearity thing, and we zoomed in on it. And if it was a smooth curve, we zoomed in, we zoomed in, we zoomed in, we zoomed in, we zoomed in. It looked like a line, right? And then we did it with a V. Remember the absolute value graph? We zoomed in on the absolute value graph near 0. We zoomed in and we zoomed in and we zoomed in, and no matter how much we zoomed in, we couldn't make it look like a line. Why not? Because it was a sharp corner. Okay? That kind of connects to what we're about to do. So it's really writing the equation for the tangent, solving it for y. That's all you're doing today. But I'm going to encourage you to write down a few things here to help you with the process. Okay? So, find the linearization. And linearization, again, linearization is a fancy word for tangent line approximation. So really, find the equation for the tangent for the function f of x equals the square root of x at x equals 100. You're finding a tangent line. You're going to use it to approximate some values. Okay? So, I would encourage you to do this a couple of times. Will you write this down with me? L of x is equal to f of a plus f prime of a times the quantity x minus a. That's really just a fancy way of doing point-slope form for the equation for a tangent. Good so far? Okay. We are going to substitute for the a. We're going to substitute, well, I guess that takes care of f of a and f prime of a then too, right? So let's identify in the problem what is a. What a value do we care about? 100. We're going to let a be 100, and that's going to be represented on this picture. Here is that. We'll do f of x in black. F of x is the square root of x. It looks like that no matter how far you zoom in or zoom out. And we will say at some value a, in this case a is 100, that this is the point we care about, and that is 10. This graph is clearly not to scale, but that's okay, right? This is the tangent line approximation. That blue thing is the linearization. It's the tangent line approximation for the curve, and that tangent line, and again, that linearization is useful for values that are close to x equals 100. If I was going to try to find the square root of 67, would I use this tangent line? No. If I wanted the square root of 67, I'd probably use an a value of 64. Does that make sense? So the tangent line we're about to find is it's a generalized tangent line, but it's going to be, it's a generalized approximation, but it's going to be specific to that region close to x equals 100. Okay? So let's plug some things in, substitute, if you will. L of x is equal to, do you know f of a? 10. It's a pretty easy one because it's a pretty easy function. It can get a little more complicated, but not a lot more complicated, because the point of linearization is to find approximations when you don't have a calculator with you. Okay? We need to find f prime of a. In order to find f prime of a, we need f prime of x. F prime of x, the function is the square root of x, aka x to the 1/2. We did this one on Friday, didn't we? That's 1/2 x to the negative 1/2. Easier to evaluate as a radical f prime of x is 1 over 2 times the square root of x. We let x be 100 because that's the a value we care about. F prime of 100 is 1 over 2 times the square root of 100. That is more popularly known as 1 over 20. Inside parentheses now, because this is a linear equation, the x needs to stay in. I think it's good to remind yourself of that. And the a value goes in here as 100. I wouldn't simplify this. I'd let it be. You don't need to get it in y equals mx plus b form. Doesn't really help you that much. That's our linearization. That blue equation is the tangent line approximation that I wrote there in the graph on blue. Is this a new skill yet? Not really. We're just naming it something different. Okay? Do you believe me that the blue line is a pretty good approximation of the curve? Sometimes or always? Provided that we're close to 100, it's a really good approximation, right? So, knowing that, I want you to try this one on your own for a minute. I want you to find L of 101 and L of 99. Because those should approximate the square root of 101. This should be the same, shouldn't it? Right? This statement is what we're going for. The square root of 101 is the actual function value on the black curve. But if we agree that the blue line is pretty good, we can use it. So will you try those? Take about 30 seconds and see if you can find those two values. Won't go through all of the work here, but you should have gotten 10.05 or 10 and 1/20th. And here you should have gotten 9.95 or 10 minus 1 over 20. Now, will you just humor me and humor yourself just for a moment and take your calculator or computing device of some sort and just go ahead and plug in to your calculator the square root of 101 and the square root of 99 and just convince yourself that our linear approximation is pretty darn good. Again, this is more for you than anything, but what do we get on the calculator? What do we get on the calculator for the square root of 101? 10.498. Oh, even better. 10.0498. I would say 10.05 ain't bad. Well, I know, good. It's not perfect, but that's why it is called a linear approximation, because it's close. What about the square root of 99? Again, pretty darn close. I don't think it's worth spending a ton of time to figure out the error, so we're not going to do that today. And we're not going to worry about it. No. Not that I'm aware of. If it changes, I'll come back to you and let you know formally. Okay? In writing, I'll let you know formally in writing. Okay. Excellent. All right. That's it for today. But can I walk you through one homework problem? Would that be helpful? I picked one that I want to do. I'm going to start you with 38 because I think there's an important point to be made that I'm not 100% sure I made already, but I think I may have. I was going to do 37, not 38. Sorry, guys. If you started on 38, erase it. I'm going to do 37. We are on page 300. This is 4.5, day 2. And this is problem 37. Will you find that in your book, please? This is a B, C, and D problem. There's 4 steps, 4 parts. Part A. Actually, let's do this. It gives us this function. F of x is 2 divided by x, and we care about a equals 1. Okay? Part A says find the linear approximation L to the function at the point. So we're going to find a line that behaves like the curve, more popularly known as a tangent line. So we will write f of x for derivative purposes as 2x to the negative first because it's going to be easier to differentiate that way. Okay? Please write this down. Every homework problem you do that requires it, I think this helps. L of x is equal to f of a, that's the y value, plus the slope times the change in x. This is just dx, or delta x right there. Isn't that nice? This is a y value. This is a delta y value. Okay? So, we need f of a and f prime of a. Let's do f prime. F prime of x is negative 2x to the negative 2. Power rule, right? Question. Yeah, sorry about that. That's f prime of a. Thank you. Good catch. To give you candy or something for finding an incorrect. Except that would be too generous. I don't have candy for you. Okay, there's f prime of x. So the things we need are a, f of a, and f prime of a. We good with f prime of x? And we're good with a equals 1. So let's find f of 1. That's 2. So the y value we're dealing with is 2. The slope value we're dealing with, f prime of 1, is negative 2 over 1 squared, which is negative 2. The linearization then is L of x is equal to 2 plus negative 2 quantity x minus 1. That is our linear function that approximates the curve 2 over x. We've done part A. Could you simplify? You could. Do you need to? No. I think we're okay. Okay, that's part A. Part B asks you to graph the function and the linearization on the same set of axes. Do you know what 2 over x looks like? In particular, close to x equals 1. What's 2 over x look like? It's y value of 2 at x equals 1. What behavior does it have around there? It's like the 1 over x graph with a vertical stretch, right? So it looks like that. The other side of the graph would look like down here, but we don't really need that, so I'm not going to incorporate it right now, because we really only care about x equals 1. That's 2 over x. That's f of x. Okay? Now, using some old school graphing techniques, this is a line that we are going to graph. It goes through the point 1, 2. 1, 2. Are you surprised? No, you're not surprised it goes to that point, are you? Why are we not surprised it goes to that point? Because it's the tangent through that point. Good work. Okay? It has a slope of negative 2. So I'm going to go here, here, here. It's going to go through all of those points. This is L of x. Okay? That's part B. Part C. Interpretation question. It says, based on the graphs in part B, which we just drew, state whether the linear approximations to f near A are underestimates or overestimates. Will L near this in this region, will L be an underestimate or an overestimate of the actual function value? Underestimate. Why? Underestimate. The algebraic reasoning is that L of x is less than f of x near A. And I heard somebody defend it already. What's the calculus argument? The graph is concave up. Graph is concave up. Whenever the graph is concave up, and I don't think you need to memorize this because you can draw yourself a quick picture anytime you want. Whenever the graph is concave up, the linearization will be an underestimate. Whenever the graph is concave down, the linearization will be an overestimate. Okay? And we'll draw pictures for that in just a second. Part D says, it says compute f double prime of A. My goodness, this was f prime was negative 2 over x squared, right? So f double prime of x That's negative 2x to the negative 2, so that's 4x to the negative 3 using power rule. So the double derivative is 4 over x cubed. And we care about x equals 1, right? A equals 1. F double prime of 1, it's 4 over 1 cubed, which is 4. So F double prime of 1, it's greater than 0. Therefore, we have concave down. I'm sorry. Greater than 0 means concave up, guys. Sorry. Concave up. Okay? And I don't think that's worth memorizing, that whole concavity thing, because if you ever forget, draw a curve that's concave down and draw any tangent line you want on it. The tangent line will always be an overestimate, no matter where you draw the tangent on a concave down. Draw a concave up. In case you forget, anywhere you draw a tangent on a concave up curve, your linearization is going to be an underestimate. Okay? Your assignment, and I think I updated this on Friday, is 4.5 day 2.